Welcome to the lesson 33 of industrial instrumentation. In this particular lesson, we will study the flapper nozzle, or rather flapper nozzle system. Flapper nozzle is a very important item in most of the pneumatic systems or pneumatic based instrumentation, because as you know that even though we are many sensors and all those things are converted to the electronic domain, but still in some cases we need this pneumatic system for the safety reason as well as for the large controlling the large control valve and all those things. And especially in the petrochemical industries or hydrocarbon industries, where the electronic systems or electrical system is forbidden to use, because there is a voltage rating which should be not it should not be above 45 volt. In that system also we need this flapper nozzle system. Now, flapper nozzle system, the advantage is that you see that it has a it can be used as a displacement sensor, it can be used as a differential pressure transmitter and so on. We will discuss all these things in details. Let us look at the content, introductions, then we will go to the principle of operation, then we will go to displacement measurements and displacement sensors. Rather, we will see there how the flapper nozzles can be utilized to make the displacement sensor. We have a reverse acting pneumatic relay, because you will see that to make the keep this pneumatic sensor flapper nozzle systems in a linear region, we will find that we should make the movement of the flapper very small. So, to do that thing we need some pneumatic relay. So, we will discuss this in details, which is called reverse acting pneumatic relay. Then we will also see the current to pressure converter or I to P converters using the flapper nozzle systems, how we can make I to P converter, because in many in the process always we need to I to P converters. Many cases we will find that whether the 4 to 20 milliampere of current we have to convert to 3 to 15 psi of pressure. So, in that type of situations we need this I to P converter. Then differential pressure transmitter, this also we will discuss in details, because differential pressure transmitter, as we know that we need it in many process, and though we have now electronic system, but still this pneumatic differential pressure transmitter is still used in many process industries, right, because as we have studied during the flow meter, that in the flow measurements the flow is calibrated in terms of pressure, right, differential pressure that is to be transmitted. We can transmit 4 to 20 milliampere, but we can transmit to directly 3 to 15 psi pressure also. So, we discuss this thing how we can make with a flapper nozzle system a differential pressure transmitter. Basic introduction. Flapper nozzle is one of the most versatile device. It finds its application as displacement measuring devices in differential pressure transmission and as an IP converter. The basic principle, which is the movement of flapper depending on the air pressure coming from the nozzle, remains the same as in each application. In all applications we will find there is a nozzle, and through which the continuous air is bleeding through that nozzles, and we have a flapper. This nozzle position is fixed, but the flapper position is variable. Now, we will find that if the flapper position varies, we are getting some pilot pressures or back pressures. So, which can be utilized, which can be calibrated in terms of pressure, currents and so on, right. Application as a displacement measuring devices. Let us look at the displacement measuring devices, how the flapper. Now, to know the displacement measuring device, let us first look at what is this flapper nozzle system looks like. A flapper nozzle system is used for the measurement of small displacement. A small movement of the flapper can result in a large change in the output pressure, and hence it is treated as a displacement to pressure converter. Okay. Basically, I am getting pressure. Please, all the flapper nozzle system, please note the output is pressure, whether it is I am measuring the displacement or velocity or current, output is in terms of pressure 3 to 15 psi, or it is whatever in kg if you say. It does not matter. So, its output is pressure. So, that it is treated as you look at the last line, and it is treated as a displacement to pressure converter. Such transducers are designed for use on both hydraulic and pneumatic power supplies. It is used as a pneumatic and hydraulic power supplies. The pneumatic system is operated at an air pressure range of 15 to 30 psi. I am talking about the supply pressure, but we will find that the pressure with controlled output which we will get from the, or the range of the output which we will get from the pneumatic system, our flapper nozzle system is 3 to 15 psi. Flapper nozzle system, let us look at, this is the basic flapper nozzle system. So, you can look at very carefully. Okay. You see here that we have one, this is our nozzle, it is small in diameter, it is a circular in nature, right. There is a nozzles and this is a flapper which moves in these directions, as you can see it is written. So, it moves in this direction, you can see here. Now, you see there is a continuous flow of pressure which is called the supply pressure of air, and there is a fixed supply restriction. These restrictions will make a constant pressure, okay, which is constant PS. I mean it will make a restriction, so that you will get a constant bleeding of air through this nozzle. Now, you see that if the flapper goes out, if the flapper goes in this direction, if the flapper moves in these directions, you will find the more air will leak through this nozzle. This is the nozzle which is in circular in shape, this is the nozzle, I mean the more air will. So, this will reduce the pressure P naught. Now, obviously, please note that PS will not change, that means the supply pressure will not change, but these back pressures or pilot pressure will change, this PO will change, it has some temperature TO, okay. It might be different from the supply pressure temperature TS, it does not matter, right. Now, if it moves in this direction, the flapper moves in this direction, as if I use it as a displacement sensor. If it displacement sensor, obviously I will put the displacement to the flapper, is not it? This is a hinge here, so it moves in this direction, okay. So, either it will go in these directions or it will go in this direction. These are neutral positions what we have in the flapper, right. Now, you see that when it moves in this direction, so it will allow less air to leak through this flapper, because there is a continuous bleeding, because supply pressure PS is coming. So, this will lead to the increase of the pressure PO or output pressure. These output pressures will be calibrated in terms of not the temperature, output pressure will be calibrated in terms of the displacement. This is the basic principles of the all flapper nozzle systems. So, you will find that whether it is a temperature, current, it does not, I mean current, it does not matter, you will find that everywhere this is the basic principles. This is the output PO which used to be calibrated in terms of the process parameters we are measuring. Here the process parameters we have taken as a displacement. Clear? Now, let us look at the ambients, I mean this what the regions we are talking about. P atmospheric is the atmospheric pressure, okay. Then xi is the displacement of the flapper, if you look at xi is the displacement of the flapper. Gu is the outlet mass flow, we are considering here mass flow also, not the volumetric flow, the mass flow of air. Gs is the inlet mass flow, right, inlet flow from the supply pressure which is coming from. Then we have a PS and TS is the pressure of the supply air and its temperature, pressure of the supply air and its temperature. Then PO is the pressure output, okay. Also it has a temperature of T naught, that we have not mentioned in the region, okay. So, it is always bleeding to the atmospheric pressure, clear. The output pressure of the nozzle back chamber is measured by a pressure sensor. So, you can use many pressure sensors, we have studied so many pressure sensors. So, I can use to measure the pressure by any gauges like diaphragm gauges, these that we have studied so many. So, we can use utilizing I mean any principles, we can make a diaphragm gauge one of the most suitable, diaphragm gauge also can be used, okay, pressure sensor. The flapper nozzle system shown in the figure, that means figure 1, consists of a chamber of small volume connected to a constant pressure source which is PS on one side and vented or bleeded on the other side to the atmosphere through a nozzle. Okay, this is a basic principle. If you say what is the flapper nozzle system, you must write this line. That means it is saying that the flapper nozzle system, which is consists of a chamber of small volume connected to a constant pressure source on one side, which is supply pressure, and vented or breathed on the other side to the atmosphere through a nozzle. The flapper in front of the nozzle is used to regulate the rate of airflow bleeding out through the nozzle to the atmosphere. As I told you, we have explained that how the movement of the flapper will regulate the rate of the airflow or air, which is bleeding to the atmosphere. When the flapper is held tightly against the nozzle, no air leaks out, and ultimately the output pressure PO reaches the value of the supply pressure, right. Obviously, is not it. When I tightly, that situation never arises in a flapper nozzle system. That means, if the flapper, if suppose I have a flapper here, so I have if this is the flapper, this is the nozzle through which the air is continuously, I have a supply pressure on this side. So, suppose this is flapper is now moved and we have controlled, we have totally stopped it bleeding. Then what will happen to the PO output pressure? Output pressure will be equal to the supply pressure, is not it, because nothing is vented to the atmosphere. So, the output pressures PO will be equal to the supply pressure. When the flapper is held too far away, it has no effect or control on the output flow rate, and the flow rate is governed by the system size and configuration. That is also it is more important. This will tell you the range, total range of the flapper nozzle system. That means, total range of the displacement sensors which are going to design. What I am saying, if it goes away from the far away from the nozzle itself. So, that suppose I have a nozzle, so flapper goes away this one. So, that time there is no control, that means, if I move like this one, there is no control over the bleeding of the air, because ultimately by the movement of the flapper I have to regulate or control the air which is coming out from the nozzle. If I can't, then obviously there is no control. So, wherever position you put it, so it has no output pressure will not change. Okay. That time continuous bleeding of the air through the atmosphere, so it depends on the system geometry or system size and configuration. As a system is designed for measurement of the displacement, the supply side restrictor and the nozzle are so designed that the output pressure never falls to the atmospheric pressure, even with the flapper held far away. Okay. It is to be done like that, so that you have to regulate the movement of the flapper in such a way. So, the output pressure will never come to the atmospheric pressure. Now, if this is the flapper nozzle characteristics, if you look at, we have plotted here on the x axis the P naught by Ps, okay, normalized, you see this normalized, we have normalized pressures we have plotted here on the y axis, and the x axis we have plotted, what we have plotted? We have plotted the displacement of the flapper from the normal positions. If you look at, you see the graph looks like this one, right. Ps is constant. If the PO increases, then what will happen? That means, it is the distance from the flapper, distance of the flapper from the nozzle getting decreased and decreased. This is side we are avoiding, you see this portion, that means it is very close to the tight positions or stopping the bleeding of air. So, you see it is coming horizontal. After that is when it is far away, when the flapper is far away, you see the xi is greater and greater. So, it has a constant value of the PO by Ps. So, we will be more interested in this linear region. If we look at, we will be more interested in this linear region of the flapper. We will do the calculations later on, fine, right. So, you will find that these pressures, with these pressures, the PO by Pa will this will corresponds to a pressure of 3 to 15 psi, okay, for some predicted displacements of the flapper. The above shows small change in the displacement. If you look at the graph, the plot, that means fall or the slope, the above shows a small change in the displacement produces a large output change. Small change in the displacement produces a large output change. Supply side restrictors, we have two type of restrictors. We have a supply side restrictors, we have a load side restrictor. Load side, that means on the flapper side, that means and supply side means which is as restrictors, and from the supply of the air which is coming into the flapper nozzle system. You see here estimations, the parameters from the experimental flows. You see here we have mass flow rate, we have plotted here GS. This is a sonic flow or choked flow, and this subsonic flow, you see up to this, and after this it is falling down, and PS is a supply pressure, PO is some mid position of the flapper systems where the pressure is coming out. Okay. Now, what are the legends? Let us look at. Now, load side restrictor looks like this one, you see here for different position of the xi, okay, for different position of the xi. If I change the GU, if I change the PU, how my GU will change. So, we have plotted like this in this particular graph. This is supply side restrictor, same things again we have plotted. Slope is, it is, I am sorry, it will be slope E, K and X, GU we have plotted, and Xi is a displacement. So, what is this lesion? Let us look at, let us look one by one. In the neighborhood of the operating point, we can do a linear approximations. That means at the linear point, that means if I look at, that means if I look at, that means the plot is, sorry, no, I can take some other pages, so some other color. You see, so the restriction is length. So, I can approximate these positions and I can take this as a linear region. This actual operating point of the, this will corresponds to 3 to 15 psi of pressure as a controlled output, clear, of the flapper nozzle system. In this neighborhood of the operating point, we can do a linear approximation. We can assume that the system is a linear system. Now, we are writing GS equal to GSPO equal to GSO. What are the legends? I will explain. Plus derivative of GS with respect to PO at PO equal to POO multiplied by PO minus PO, which can be written as GSO plus KSF POP, where now the legends we are explaining, which corresponds to 3-4 slides which I have shown. GSO is the value of GS at equilibrium operating point, PO is the value of PO at equilibrium operating point, right. POP is a small change in PO from PO. So, there is a small change from the equilibrium point, because now there is a displacement. So, that is point I am the output pressure. So, we are writing POP. KSF is the value of DGS by derivative of GS, okay, supply side I mean restricted, DPO at operating point. So, we can write GUS equal to GU PO XI equal to GUO plus KNP POP plus KNX XIP. GUS is the value of GU at equilibrium operating point, and XIP the small departure from the equilibrium operating point. Therefore, I can immediately write that GU equal to GUO plus del of GU plus DPO DPO. I mean del of GU with respect to PO at xi 0 and p 0 multiplied by PO minus PO plus del of GU with respect to xi. One side we are making the derivative with respect to, this is all partial derivative with respect to the output pressures, and other side with respect to the displacement. Okay. So, that is we are multiplying the relative displacement or change of displacement xi minus xi naught. Similarly, here the change of pressure PO minus PO. What is GU GS? Already we have explained. Now, we know that in a flapper nozzle system, mass in, which is mass in means mass of air flow, which is coming in minus mass out, obviously the additional mass stored inside the flapper, inside the nozzle, okay, inside nozzle system I should say, right. So, if I write, there is obviously I can immediately write the equations, which is GSO plus KSF POP dt minus GUO plus KNP plus multiplied POP plus KNX XIP all multiplied by dt. Now, from the gas theory we know that POV equal to MP RT naught. So, that we can write immediately V by RT naught equal to dP. Let us assume that the GSO equal to GUO, that means that the initially that the supply which is coming GSO, the mass flow which is coming in and going out, mass flow rate, it is same. So, if it is same, then obviously we can assume that V by RT naught derivative of POP with respect to dt t time KNP minus KSA POP plus KNX into XIP equal to 0. Let we assume some, introduce let us some constant k equal to minus KNX upon KNP minus KSF, and tau time constant equal to V by RT naught KNP minus KSF. or obviously if I make little manipulations, so it will give you tau s plus 1 POP equal to k xip. So, this will lead to a first order differential equations or the if you look at the response POP with respect to xip will be equal to k upon tau s plus 1. Thus, we see this about it is a first order system. So, I can say that the flapper nozzle system is we can consider as a first order system. It is also a reverse kind of transducers. That means if I forcibly if I change, because there is a spring action. So, if I change the pressure, so obviously change the bleeding pressure there which is coming out, obviously I will get a displacement there. That is the reason we call the reverse kind of transducer. It is very fast acting amplifier with good resolutions. I mean talking if you consider the pneumatic amplifiers. So, it is a fast acting amplifier with good resolution. Sensitivity is also quite high, that we have already seen. And from the graph also we can predict that it has a good resolutions used in precision measurements. So, obviously for very small displacements I can use this flapper nozzle system, because we have seen that we are getting a large change in the, for small displacement we are getting a large change in the normalized pressure output. Construction. Nozzle diameter is typically 1 by 32 inches, which is 0.8 millimeter. Volume is 1 inch cube, which is around 16 cc, it is quite small. Supply orifice diameter 1 by 16 4th inch or 0.4 millimeter, which is called fixed side restriction. Value of K is typically 8000 psi per inch, because this will give you a static sensitivity, right. Now, if I draw the electrical equivalent circuit of a flapper nozzle system, so we can represent it by a simple RC circuit. Okay, so, the analysis will be easier if I can represent by a simple RC circuit. Okay, it is very simple. I mean variable resistors, whether the, if you look at the load side restrictor, you will find that there is a variable resistance which I can replace by a potentiometer or a rheostat, and at the supply pressure restrictors we can represent by a simple resistors, and the volume we can represent volume of the total volume of the flapper nozzle system we can replace by a capacitor. So, keeping all this in mind, we got the following electrical representations of our flapper nozzle system, which looks like this. You see, this is our flapper nozzle systems. These Ri and C, Ri is the input side, that means supply side restrictor representing, and this is RO is a load side restrictors. I am giving Vi, we are giving Vo. These are electrical representations of our flapper nozzle system, where RO is a variable restriction, Ri is a fixed restriction. What is the fixed restriction? That is at the input side, the restrictions which you are getting, that is the fixed restrictions. Then C is the capacity of the systems, that is the volume. So, these actually make our flapper nozzle system. The transfer functions, so easily we can find the transfer function of the electrical system is given by V naught by Vi into S R naught Ri plus Ro 1 upon 1 plus Sc multiplied by Ro into Ri upon Ro plus Ri. You see here, let us redraw the equation, the flapper nozzle systems. We have just redrawn, we have changed the position, it does not matter, it can be flapper can be this side, this can be that side. I mean the nozzle can be, the supply air can be this side or that can be that side, it does not matter much. You see the same circuit, I mean flapper nozzle diagram, because we refer to this, that is the reason we have redrawn this in the figure 7, right. Now, let us, how will I compute the static sensitivity of the flapper nozzle systems? Let us redraw the flapper nozzle system as I told you in the figure 7, that just we have redrawn the figure. Okay, it is same as the figure 7, there is no difference. For static sensitivity calculation, the flow through the restriction is assumed to be incompressible, right. Flow through the restrictor is incompressible. First we assume, in many fluid dynamics method we have seen that we have assumed like this one, right. Now, flow through the fixed restriction is given by F1 CD1 pi D1 square by 4 root over PS minus PO, which is equation number 1. Clear? Where did I get this equation? Very simple, I got this equation from our basic orifice, orifice principles. Bernoulli is using the Bernoulli principles, we will get this one. Let us go look at what is d1 and what is. You see, d1 is the supply side restricted diameter, orifice diameter, and d2 is the load side restriction diameter, which is circular in nature. Okay. So, CD1 is the flow coefficients on the supply side and CD2 is the flow coefficients of at the load side or the flapper nozzle side, right. If I have that thing, obviously equation looks like this. Okay. So, CD1 is the discharge coefficient of fixed restrictions, that means supply side restrictions. PS, PO you know, there is output pressures, and PS is the our supply pressure. As nozzle, the discharges air to the atmosphere, the flow through the nozzle is, as the nozzle flow discharges air to the atmosphere, again the flow rate, instead of volumetric flow rate I am talking about, it is mass flow rate, I am talking about the volumetric flow rate through the nozzle is will look like F2 equal to CD2 pi D2 into x dot into P naught. Okay. This equation, this side is slightly different. We have seen that this is instead of, we have taken the circumference multiplied by the x naught, that displacement, that is we are taking at the bleeding volume, right. Let us look at. Here CD2 is the discharge coefficient of the nozzle, x bar is the distance of the flapper from the nozzle. Okay. So, distance of the flapper of the nozzle multiplied by the this pi d2 will give you the flow. Clear? If I have that thing, so obviously this is again, I mean, it's coming in a meter square or something like that. Now, I will assume that the condition of the flow continuity. Okay. What is mean by the flow, I mean equation continuity, that means F1 equal to F2, and moreover we assume the two discharge coefficients will be same, even though there is a lot of assumptions. For simplifications of our calculation, let us calculate CD1, that means CD1 equal to two discharge coefficients of same, and also assume there is a flow continuity is there. Then equation 1 and 2, if I then combine this equation 1 and 2, we will get that 16d square into x bar square by d1 to the power 4 equal to PO equal to PS minus PO, which will give us PO minus PS 1 upon 1 by 16 d2 x bar d1 square whole square. Let us look at how did I get this thing. Let us take a blank page, or let me take this one. It will look like this, you see, F1 equal to CD, because we have assumed that CD1 equal to CD2. We assume like this, and take a thinner pen, I think that will be better. That means CD1 equal to CD2 and F1 from the supply side equal to CD equal to, we write CD. This will be equal to CD pi d1 square by 4 root over PS obviously will be more than PO. So, PS minus PO, and the nozzle side flow rate we can write CD again multiplied by pi d2 2 pi r. So, instead of 2 pi r I am writing pi d2 into x bar. Okay. X bar is the movement of the flapper from the nozzle into PO. Okay. Since we know that F1 equal to F2, so we will get 16d 2 square x bar square into PO divided by d1 to the power 4 PS minus PO equal to 1. Okay. So, this will lead to 16 d2 square x bar square PO by d1 to the power 4 Ps minus Po, right. So, I can write Ps minus Po by Po equal to 16 d2 square x bar square Po divided by d1 to the power 4. So, this will lead to Ps by Po equal to 1 plus 16 d2 square x bar square upon d1 to the power 4, right. So, I can write that Po by Ps, if I take a new page, Po by Ps equal to 1 upon 1 plus 16 d square d2 here I write x bar here I write by d1 square to the power whole square. This is our equations. Okay. This actually we have explained in the our ultimate equations in that is normalized output, how the normalized output is relates to the displacement, right. So, this is our expression 1 upon 1 plus 16 d d2 plus I am sorry, I think that will be 16 d2, because if I take 16 inside, so it will be here, it will be 16 if I, so it will be here if I take 16. So, this will be and let me write down this equation. This will be, let me take pen. So, this will be like this one, P naught by Ps 1 upon 1 plus 16 will take outside, then I will get d2 x bar by d1 square to the power whole square, right. This is my final equation. Anyway, as you have seen. Now, assumptions made for arriving at equation 1 and 2 are involved. There are, what are the assumptions, basic assumptions we have taken. The velocity of approach is neglected. For small x bar, the area of the nozzle outlet to the atmosphere is taken as pi d2 into x bar instead of pi d2 square by 2. Okay, pi d2 square by 4, we have taken pi d2 into x bar, because we have seen that it is a variable, that is the reason we have taken like this one, whereas in the supply side restricted we have taken pi d1 square by 4. That is a simple orifice formula we have taken. The normalized response curve is shown in figure 8. What is the figure 8? Let us look at. This is a normalized response curve. Let us look at very carefully. This is our plot Pn normalized, output by input P naught by Ps, xn bar, this is also we have plotted in the x axis, which is d2 x bar by d1 square, right. This graph is very important. This will control the entire position. You see here, if I come down, so obviously what will happen, if I come to the close to the nozzle, when the flapper moves close to the nozzle, that means you will find that the output pressure is increases, which is supposed to be. So, this is a normalized response curve. From this curve we will do so many other things. Now, response slope dPn by dxn is approximately linear for short xn and Pn ranges. What is that? You see here. So, dPn by xn, that means this slope which is supposed to be actually, if I say that it is this slope is actually, if I take a thicker pen, this slope is equal to actually that dPn by dxn. Okay. So, this slope is actually will give you the response of the flapper nozzle system, approximately linear for short xn and pn ranges. For very small ranges we will find it is linear. This is very important. So, we need a linear relationship. Right from the beginning we have seen in many all instrumentation cases we need a linear relationship. The maximum slope for sensitivity is obtained by equating the d square pn from basic basic elementary of our calculus. We know d square pn by dxn square equal to 0, such that xn bar equal to 0.144, right. That is a value for which you will get the maximum. So, which gives dPn by dxn bar equal to 2 minus 2.59, and this means this minus sign signifies that the slope is negative. That we have seen from the graph, the slope is negative, and Pn equal to 0.75. Negative sign indicates the slope is negative. When xn bar is sufficiently large, Pn becomes constant. That we have seen when it is coming, it is a constant, right. When xn bar is how does it look? You see, we have seen how does it look? It will look like this one. You see here, if I take a blank page, so the slope will look like. So, if I take this one, that already we explained, becoming if you do not take that much. So, it will look like this one. So, the pressure is xn is far away, bar is far away, you will find that it is becoming constant. So, it is the pressure is constant, that means PO by PS is constant here. Okay. If I take different pen, sorry. Right. So, it is coming like this, slope is looks like this one. So, PO by PS is constant to this value, right, when xn is large. Clear? So, to avoid this zero sensitivity portion, that the lower and upper limits or bounds are fixed to Pn equal to 0.75. Okay. Normalized output is 0.75 and Pn equal to 0.15. Because I cannot take Pn equal to obviously 0, I mean it is a Pn 0 means it is not possible. That means that is this I am talking about. So, I have taken a range of Pn equal to 0.75 to Pn equal to 1.15. For supply pressure of 20 psi, we will find that this will lead to PO to lie between 3 to 15 psi. Okay. For Pn I cannot make it 0. So, if I make it 0, there is a problem. So, that because we need a continuous bleeding of air through the nozzle. So, I cannot make it 0. So, Pn I make the PS 20 psi for the supply pressure of 20 psi, this will give to 3 to 15 psi. This is the key reason you will find in all the pneumatic systems always we are getting this value. Many a times we are calling the industry standard is 3 to 15 psi of the control pressure, where it came from actually. Okay. This is the reason why it is, this is the point where it actually came from, right. So, 3 to 15 psi, because why I want to make it within this range, because this will take the linear portion of our graph. So, the flapper nozzle system will be linear in this region, that is the reason we are limiting this pressure. The upper limit is fixed mainly by the pipe thickness, the lower is not kept 0 to enable positive check on the control pressure on the low side, as well to avoid the leakage, any leakage from outside into the system. There should be always some bleeding. So, that is the reason why we are saying there. So, there is no, if there is not bleeding, there is a chance of the output pressure will come, output atmospheric air will come inside the system. So, that we do not allow. So, that is the reason we have always leakage. Okay. To always there will be some bleeding of the air from the nozzle to the atmosphere. Flapper nozzle with air relay, this is another important thing. In order for the flapper nozzle to work satisfactorily, the pressure changes must be small. We have seen that the pressure change must be small, so it is very small, right. This is accomplished by using an air relay. It is excellent thing. You see how it works. A controlled pressure of 3 to 15 psi obtained from the relay by a process pressure change of only 3 to 5 psi, and this involves only 1/6 of the original movement of the flapper. So, I am strictly I am bringing the because I am saying that 3 to 15 psi, but I am saying that if I can even reduce the movement of the flapper to a smaller to this value, then what will happen? I will get a less pressure. We will find that the pressure changes in this type of situations will be 3 to 5 psi, but with the relay I will make it to 3 to 15 psi, which is the industry standard. How it looks like? Let us look. Here the flapper position is directly proportional to the pressure change. In other words, the system is strictly operated in the linear region. Okay. The schematic shown in the relay is, you see this is the relay position, this is our, from the process there is a bellow, you can see here, okay. There is a bellow. So, if the pressure increases, this flapper will move further here in this direction. Okay, let me take this bellow will move in this direction. The flapper will, because this is a fixed end of the bellow, the bellow, the flapper will move in this direction. Vertically, it will move in this direction. Horizontally. If it moves, then what will happen? You see that the more air will leak out. More air will leak out. This will reduce the pressure here. If we reduce the pressure, this will what will happen, you see that ultimately it will reduce the inside pressure inside this diaphragm gauge. So, this diaphragm will come down. If the diaphragm will come down, what will happen, you see diaphragm will come down. So, this ball will come down. So, allowing the more pressure, allowing the more pressure to indicate. So, that means the more signal to the remote station. Okay. So, this is the basic principle. Right. Other way, if the flapper moves in this direction, this will increase the flapper. So, it will move this in this direction. So, if it moves in this direction, the supply less air will come to the gauges, it will show less, right. Let us look at the air relay is reverse acting type. With the flapper moving away, the larger process, when the process pressure is large from the nozzle, the pressure Pi falls and the diaphragm comes down along with the ball D. Okay. Pressure Pi, this is the pressure Pi, because if it comes down, the pressure Pi falls along with the ball D, right. So, it is close the path B. Again, if I go back, it close the path B. So, this path will go, because this will now valve, since the pressure increases, this will move out. So, this path there is no chance of air to come. Close the path B more, and the passage between A and C is more open. What is look at? Sorry, passage between A and C will be more open. So, this will come down. If the valve is coming down, sorry, if the valve is coming down, then what will happen? So, there is a less path, so that less with the valve is coming down. So, what will happen? So, there is a less path to come here, but the more path A and C will be more and more open. And the passage between A and C is more open, giving a larger pressure indication in gauge G2. Okay. So, when the Pi falls, when the G1 is showing some lower pressure, G2 will show the larger pressure. The reading in gauges G and 2 are always inversely related. It is another way also. When the flapper is coming close, when the system pressure is less, then what will happen? Flapper will come close, then the ball will move, the G2 pressure will be high, pressure showing by the pressure showing by the G1 will be high. So, the what will happen, that the diaphragm will go up. If the diaphragm goes up, obviously it will show the less chance, less, it will restrict the air passage to the gauge G2. So, that is the reason we are telling that the G1 and G2 will be always inversely related, right. So, G1 and G2 will be G1 and G2 will be, this is G1, you can see here, this is G1, sorry, G1 and G2 will be inversely related. Okay, this is G1 and G2 will be related, inversely related. With the flapper moving away, that is already we have explained. Now, as the output pressure PO is derived from the supply pressure PS, the highest reading is limited by this factor, right. The air relay gives this amplified output for a small change in pressure signal. Air relay will give amplified output for a small change in pressure signal. That is the reason from 3 to 5 psi, I am getting a signal from 3 to 15 psi. Now, current to pressure converter, I to P converter, as I told you, this is very widely used in industry. Current to pressure transducers are used primarily in the process control to change a 4 to 20 milliampere of electronic signal from a electronic control into 3 to 15 psi for a pneumatic controller. An effective I&P must incorporate the following features. What are the following features? It must provide air to the receiver quickly, accurately and in sufficient quantity. It must be able to exhaust air quickly when the signal decreases. Sorry. It should be it should consume a minimum amount of supply air for operation. It should be easy to repair, must be sufficiently rugged to withstand difficult environmental conditions, including variations, dirty supply of air. That is not very important. Usually we can filter the air, temperature extremes and corrosive conditions. The flapper nozzle system modestly fulfills the above all criteria. That is the reason we are using the, because it is not very much affected by the temperature. That is most important in the flapper nozzle system. Now, traditional flapper nozzle system is shown in figure 10, you see here. So, this is the traditional flapper nozzle system. You see the current is coming to the electromagnetic coil here, okay. Current is coming here, current is coming here, right. So, there is a bellows, you see the what will happen, that pressure it will, if it comes down, so this will increase the pilot pressure here or back pressure, okay. So, the flapper now position of the flapper depends on the current. I want to make I to P converter. Ultimately, the position of the flapper will be corresponds to the pilot pressure, okay. This is the pilot pressure should be a function of the current, but the current actually will control the position of the flapper, right. So, this there is a hinge, you see here at the center point there is a hinge here, okay. The flapper can go this way or that means it can go this way or that way like this one. So, if it moves like this one, obviously what will happen, you see this the flapper position will change, clear. Now, input current is 4 to 20 milliampere is applied to a coil armature arrangement that acts on a beam. Beam is now the armature, okay, or flapper, whatever you call it. We are no more calling it flapper, we are calling it a beam. The beam positions itself against a nozzle, okay. So, positions itself nozzle that has the air flowing through it. The gap between the flapper and the nozzle determines the back pressure, also called the pilot pressure, that builds up in the nozzle, okay. So, this is the pilot pressures in the nozzles. We have seen what is the pilot pressures. You see here the pilot pressure. So, this gap will control the pilot pressure. The same thing we have seen that it can be supplied to a relay to get a higher, I mean that 3 to 15 psi of pressures also. You have a feedback relay also, bellows also, okay, to neutralize. The gap between the flapper and nozzle determines the back pressure, also called the pilot pressure, and builds up in the nozzle, right. You see the reason of the feedback, because it is working like a spring, because it comes very close, if the bit comes, because I have a supply pressure, if it comes very close to this one, so this will increase the back pressure, because pilot pressures and this pressure is same. So, this will increase the more pressures in the bellows. So, it will make the system so that it will restrict the nozzle to come very close, because it will work as a spring there, right. That is the reason we have used a bellows here also. So, the gap between the flapper and nozzle determines the back pressure, also called the pilot pressure, that builds up in the nozzle. A bellows is sometimes connected, a is sometimes connected to the nozzle area to balance the forces on the armature flapper. As I told you, it is just like a spring. Instead of spring, I am using a bellows there, which will control the position of the forces on the flapper nozzle system, armature flapper or armature. This is instead of flappers we are calling it armature or bar, whatever you call it. Basic principle is same, the nozzle remains fixed, only the armature is moving. The pilot pressure for linear operation is channeled to a pneumatic relay or booster. Okay, that pilot pressure or back pressures which is coming, that is going to relay for boosting operations, right. That means it will might be the pressure is less, 3 to 15 psi will make a small movement, so we have a more linear region. This will lead to after the once it goes through the relay, so I will get a 3 to 15 psi of pressure. The pilot pressure, okay, the booster or relay acts as an amplifier, translating the low pilot pressure into higher output pressures and capacity. Okay, because the capacity is also important, because if the capacity of this system might be very small in this case, we have higher capacities, we can use both the capacity and range. I can go to the booster circuit or relay circuit. Mechanical I to P converter, that means current to pressure converter, that use a flapper nozzle and which do not use electronic feedback sensor face some difficulty in dealing with the environmental factors. What are those factors? Let us look at. The flapper is susceptible to vibration and traditionally has forced users to mount the IP and current to pressure converter separately on a pipe or rack. This requires additional tubing to carry I to P output signal to the valve. The additional cost nullifies the benefit from the mounting the I to P converter together in a common location. The dead time and lag time introduced into the loop by longer output signal tubing has a significant impact on the loop performance, because whenever we are using some tubing in a pneumatic systems, okay, it is not very predominant in the case of electrical system, but in pneumatic system we are using more tubing. Okay, obviously, it will increase the lag in the system as well as the dead time in the system. Traditional I to P converters are also adversely affected by fluctuations in air supply, downstream tubing leaks, temperature changes and aging of the magnetic coil within the I to P converter. Periodic calibration checks are required in order to maintain the output of the I to P converter within the desired range. Dirty supply air is a major cause of I to P downtime. Mechanical IPs do not have electronic feedback to compensate for partial plugging, but by designing the nozzles opening to be at least 0.04 centimeter, that means 0.015 inch diameter, this problem can be avoided. Now, there is new type of I to P converters has been introduced. Let us look at that I to P converter, though there is a basic principle is again the flapper nozzle system, but with the help of piezoelectric systems we have used. Several new concepts have been introduced. These new concepts have changed the nature of the pilot stage and have incorporated sensor based electronic systems. It includes some trade offs like between efficiency and cost or improvement of one factor, which leads to the degradation of the other. One such important device is piezo ceramic bender nozzle. So, piezo ceramic bender nozzle, you find that piezo, you know that there are, we can have your natural systems. We have natural piezoelectric systems, we have a synthetic, we have a piezo ceramic also. These are some advantage of the piezo ceramic systems. So, let us look at that. Now, piezo ceramic bender nozzles, you will find that it device is shown in figure 11. The unit does not use the coil to move that flapper, which you have used in the conventional I to P converter. There is a coil actually which energizes and which current is coming to that coil, and it is giving the movement of the flapper. But instead the flapper itself is made of layers of different materials which are laminated together. These different materials flex or bend when the voltage applies across them, right. The 4 to 20 milliampere of current input signal to the I to P is first converted to a voltage in the range of 20 to 30 volts DC, right. Now, this voltage is actually given to the flapper this design tends to be more stable in vibration than the typical flapper armature. And some of the drawbacks of this new concept are, you see that will come later on. Let us see this one. This is our figure, you see here. So, we have a lead jar current, this is our ceramic piezoelectric systems. So, now first the 4 to 20 milliampere of currents we are converting to 20 to 30 volt DC is applied. As you know, the piezoelectric system is reversible systems. If you apply the pressures, I will get a voltage. If you apply the voltage, I will get a change in pressure. So, this, since it is lead mercury and brass we are using, so it will try to bend, and these bends will be sensed by this, you see this lead zirconate and brass, and this will make the, this will work as a flapper that time, and it will come to the either to the close to the nozzle or to the off. So, this will give you this booster, this output, this is a pilot pressure, okay, which is sensitive to the, which is this pilot pressure, the booster pressures or booster control. This pilot pressure will be a function of this DC voltage we apply to the flapper nozzle at this ceramic, okay. And this voltage again it's controlled, is a function of the current which is coming, right. So, this will lead to, you see, the whatever the pilot pressures we have, back pressures I am getting here, that is proportional, or that is a function of exactly the current which you are getting. So, so many other point of the those we have eliminated here in this, because there is no coil as such. So, directly applying, and due to this there is a bimetal sort of this is ceramic and brass, obviously this will bend in one direction or the other. So, when the voltage will be applied due to piezoelectric effect, so obviously this will make the this flapper close to the nozzle or not, or away from the nozzle. The bender does not have a very good memory, that means it has a creep, okay, which memory means it is called the creep in the systems, and will tend to locate in a different position for the same input signal. This creep is cumulative and eventually exceeds the adjustment range of the calibration mechanism. An electronic feedback sensor can be combined with a piezo ceramic bender to compensate for the creep temporarily for the but the feedback circuit typically uses such more power available from the input signal, having little to energize the bender. The bender cannot balance against the force of the nozzle air unless the nozzle is kept relatively small. Thus, large nozzles must be traded for improved bender control. Plugging of small nozzles is the chief reason for I2P field failure. Force balance differential pressure transmitter, you see there we have seen that two pressures are coming this side, you can see here two pressures, P1, sorry, this P1 and P2 is coming here from the process, right, which is coming further from the flow. So, these actually from this I am getting a supply pressure which is a function, PO is a function of K P1 minus P2, because always in the flow measurements we have seen that all differential pressure based flow meters. So, this type of output pressure, this will be this P1 minus P2 or PO will be calibrated in terms of flow. So, that is we can use a total pneumatic systems, we can see this, you see there is another this is a feedback bellows we have used, this is a bellows, please note feedback bellows we have used. To block diagram, this if I draw the block diagram, it looks like this one. So, all the significance is P1 and P2 the output pressures, and the output pressure is coming here, two pressures from the upstream and downstream is coming here, which is combined. So, we are giving the relation like this one. Say AB1 AB2 the area of the bellows, KB the bellow linkage compliance, K in the flapper nozzle again, and in the above circuit P1 is always greater than P2, then the upper bellow exerts more forces than the lower one, always it will be greater because upstream flow is higher. Then thus the flapper moves away from the nozzle and the pressure inside the tube A falls. The feedback bellow cannot hold the flapper in such a position and brings it down. So, the output rest pressure will come P naught equal to AB1 by AB2, I1 by I2, P1 minus P2, right. So, this actually will give you the direct, this you see the output pressure is again the function of P1 minus P2, which is actually calibrated in terms of the flow. So, with this I come to the end of the flapper nozzle system.